So it now gives me great pleasure to introduce Janusz Adamson, who has been here in the audience before, but he's never been standing in front of us. Janusz started off teaching astronomer to marine cadets and people like that up in the north of England. And the subject that he's going to talk about tonight started with him, first of all, hearing a talk from Jocelyn Bell, who was the discoverer of pulsars in the late 1970s. And then he heard another talk by her in 2018, much closer to home, actually in Turner Sims here. And I gather that this was just at towards the start of COVID. And so this was a project that occupied Janusz during the COVID era. So he's going to talk to us about pulsars and how they might be used for ship navigation. So Janusz, over to you.
Right, can you hear me? Yeah. Right. Well, first of all, thank you, John, for inviting me to give this talk. Right, so although I've put down the contents there as to what the talk is about, this is sort of just to give you a general idea of the basic topics. But it's more to do with, as I said, timekeeping and navigation and how it's being used, or how it was used in the past. A little bit about the sextant, some of the global navigation satellite systems which help navigators, and a little bit about pulsars and how they can be then used for ship navigation. I should say I'm not an expert on pulsars. I'm just a general astronomer with a background in computations of satellite orbits. But I do have an interest in navigation, and I've used that, put the maths which was required for that to hopefully to some good use. Right, so before we get going, a little bit about, let me just give you a general scenario. The Bay of Biscay is obviously can be a very stormy place, and this scenario was set, I had to set a date, so it's set in, it'll come later on anyway, it's set a few years ago, and a ship had been hit by a wave, or it had lost its communications. There's a solar storm or some jamming or spoofing, and it's obviously adrift in that part of the world, and it's slowly moving towards Spain. So in that sort of condition, the best thing that the navigator can do is to use dead reckoning, which basically is based on a sextant reading, and obviously the information from the ship about its believed course and speed. Or just to improve any information, if they know something about the wind direction or the steering error of the ship or the current, then obviously they might have a better idea. But basically, if they've got no communications, then that is, I reckon, a fairly feasible scenario. I'll just say a little bit about jamming and spoofing. You've probably heard a lot about it. It's affected the aircraft flying around the Ukraine area. There's also been jamming and spoofing on NATO exercises in the North Sea, around Norway, likewise in the Baltic. So it is around, and it's getting serious. It is actually getting very serious, and people or the scientists, or the people managing global communications are looking for methods of trying to either overcome the jamming and spoofing, or coming up with alternative methods for general navigation. I shall go back just a minute. Right. Let's look at previous. Right, I just wanted to show this, why pulsars, and just basically one of the advantages of pulsars is that you can detect the pulsar signal at various frequencies, anything ranging from around about a few megahertz to quite a few gigahertz. So if you're trying to do any jamming, it's going to be a very, very difficult task. So that's one of the reasons as to why there is an interest in pulsars. Right, to sort of get started, I want to say a little bit about timekeeping and how did we come about with a day having 12 hours and or let's say the day is 24 hours, and where did that concept come from? Now this is my idea. I'm not saying it's true, but here is a possible explanation. Basically we've got 5 fingers, 2 hands. So you might say if you take the day, you can divide it into a morning and into an afternoon, and then you have the bit at the end, which is the night time, or the bit in the morning, which is sunrise. So effectively, the day was divided into 10 units. Now, if we weren't around, and if the dinosaurs weren't exterminated those 60 million years ago, then the people, or the aliens then, may have had 3 fingers. So they would have probably come out with a totally different system. So this is why I say that it is our invention. We've come up with this principle and it's stuck with us. So very, very simply, we have the day divided, or sun, or just daylight, divided into 10 units plus a bit in the front and a bit in the back. And the unit obviously varies during different times of the year. And then you've got the 12 units on the other side. So hence you come up with a 24 units per day. Now, in the earlier times, we needed to know where were we, how did we navigate. We have heard stories, about a lot of the early navigators using the stars, but one of the things which they may or may not have used was, for instance, a shadow stick. And what I've got here is just a very simple example of how you might be able to calculate your longitude. And this is sort of based on the assumption that you've got a timekeeper, an accurate timekeeper, and let's say in the 1700s you may have sailed from Greenwich and you sort of set your timekeeping mechanism at 12 o'clock noon. When the balloon came down from the top, that's 12 noon. And then as you sailed along, you use the shadow stick to determine when the sun was at its highest point in the sky, which was the local time, and you could see what was the difference between what your chronometer or your timepiece said and what was the actual time. The difference may have been, an hour, 2 hours, 3 hours, very much depending on where you were. So in this simple example here, we say that the time difference was 1 hour and 20 minutes. And if you go and do the various sums, noting that a second of arc is equal to 1 nautical mile, you can work out roughly where you are, what your longitude is, so many degrees east or west of Greenwich. Right, latitude. Well, again, you can use your just a general stick, an idea. And if you know that on the when we have the equinox, 31st of March, the sun has equal times. You've got day and night are of equal lengths, so the sun is at this particular point here. So if you've got some particular date before or after the 21st of March, you can work out what is the percentage altitude. So in this very simple sum, we know we are, this is where I need my stronger glasses. I should have put my stronger glasses on. You can work out what the number of days are, multiply it by the factor, and you come up with 82 days. And also, if you choose that the altitude of the sun at that particular time of year was 60 degrees, you can work out, basically by that very simple calculation, that your latitude in this case is 50 degrees. Now, I'm sorry, I'm going to have to put my other glasses so I can see some of the numbers and maybe give you a slightly better explanation. Right, again with regards to the sextant, there are several particular parameters which you use. One, you observing the altitude of the sun, and we've just given there's a particular value there. There's obviously an instrumental area. I mean, with any instrument, you've got to find out what is the general, how accurate, how good is that instrument, and we call that the instrumental error. And I've just put it down there as, in this case, example 3.3 degrees. Now the next one is dip. Well, if you're standing on a ship or standing on your boat, sailing boat, you are above sea level. So therefore, when you're looking at the horizon, you're actually slightly above that, and therefore, if you were to be at the actual sea level itself, your distance, which you can see, is about 7 kilometers or so. If you're standing higher up, it's a bit further. So the difference between those two measurements is your dip, and you have to correct for that. Now, with regards to refraction, well, that's something which you get from tables. And if you take away all those values, the altitude of the sun which you've observed is actually slightly different. And with that information, you can determine what is the latitude of where you actually are. I've put down there that if you do have a sextant, with the modern sextants, the very experienced navigators who use a sextant, they can get a positional accuracy to something like under a minute of arc. But the average value for the user and eyes, if we use this, we have something like about 2 minutes of arc. So that means the positional error is anything ranging from about 0.4 nautical miles to about 2 nautical miles. Now, the old clocks, said that with the wind-up clocks, Tudor times, the error was something like about a minute. That's what I've got. Yeah, I think I've said about a minute a day. So if you're actually if you're going by one of the ships then over to Virginia, over to the States, 90-day cruise, and you've lost about 90 minutes with your clock, and that gives you a longitude error of about 1,350 nautical miles. Right, so you think you're somewhere in the middle of the Atlantic, when in fact the American coast is just around the corner. Now, I'll mention just a little bit about Harrison, but the precision timekeepers, good timekeepers, appeared in the late 1770s with an error of about 4 seconds in 24 hours. So that means that's a great improvement on what, when actually trying to determine where you are using a chronometer. Now the reasons why where are we? Oh, I've forgotten. It'll be probably the Royal Institute of Navigation came up with the longitude prize. Was obviously the navigators didn't quite know where they were, but there was a serious shipwreck in about 1707 off the Scilly Isles. Yes, I know there are only 4 ships which went and were injured, which were shipwrecked, and over 1,300 people lost their lives. But if you go back earlier to the Armada, I mean, how many Spanish warships were lost because they went and sailed into these waters, and God knows how many people died there. But anyway, Harrison started developing his chronometer. It's a huge thing, very cumbersome, and over the years he actually managed to reduce it down in size to what you have here, a chronometer of that sort of size. This was around about in the early 1750s. And James Cook took obviously his equipment over to New Zealand to observe a transit of the moon across the sun, and and used it for various other observations, but it also used that equipment, and he was able to determine fairly precisely as to where he was. Now, the next thing which we obviously need to do if we're doing any sort of measurements, we need a reference point. And our reference point is the Greenwich meridian. Now, how did that come about? And it's purely a fluke, or maybe it was, that's the way things were, that Great Britain had the largest number of ships compared to the rest of all the naval countries, and also the greatest tonnage. As you can see by the figures there, 65% of the shipping and 72% of the tonnage, so there's just no competition. That's why Greenwich became the point where we had zero meridian. And obviously the ships, when they sailed, they would check their chronometers. Where are we? Over here. So there's a ball over there, and exactly at noon that ball will come down. But when did they know that this occurred? Well, obviously there was a transit telescope. There's only just one sort of interesting thing about this. Yes, okay, it was noon at Greenwich, but let's say if you took a train, in the early 1800s, you might leave London, let's say at midday, and you get to Plymouth 4 hours earlier, except the time in Plymouth wouldn't be 4 o'clock in the afternoon, it would be something like about 3:40 in the afternoon. So you had these problems about timekeeping. Right, so we've come up with various types of systems for navigation. This is equipment used in, at the turn of last century, going on to during the Second World War and afterwards. You had Decca, was one of the early ones, but there was also Loran, and there was a concept of trying to use E-Loran, which is the latest one, to assist in navigation in the English Channel, except as from what I heard a few years ago, that they weren't going with that system either. It's too expensive, or for whatever reason it was cancelled. But the very basic concept with E-Loran is you've got a transmitter, the master transmitter, and it'll be sending pulses, radio pulses, let's for argument's sake, every minute, and there'll be a little bit of information about that particular pulse. That means it'll give you the time at which it was sent, and you would also have slave transmitters, and you'll know the distance apart between the master and the slaves. So when you're on board a ship, you will receive the signal. You'll receive 3 signals from the 3 different transmitters. So you look at the time of arrival, and obviously the difference in time, because if, let's for argument's sake, that the 3 transmitters issued a signal at midday, they will have received the signal 5, 10, 15 minutes later. And they know that the time of the signal was midday, so if you know what is the difference in time, and you multiply it by the velocity of sound, you'll be able to work out what the distances are from the master and slave transmitters, and you know the distances between the transmitters, you can work out where you are. Now, you don't really need to do the calculation. They actually provide you with books, and from that you can work out where you actually are, and from that you determine your position. Now, the interesting thing is that there are 3 transmitters, because when we go and look at GPS, that's the Global Positioning System, which is the most popular positioning system under the Global Navigation Positioning System, you require at least 3 satellites to determine where you are. And very simply put, it's a very simple equation. I'm not going to go and explain what it is, but you literally have the changes. You know where the satellites are, you know the time at which these signals were transmitted, and what you need to do is to determine your position in terms of the coordinates. And this is just a diagrammatic representation, 3 curves, because the satellites aren't that far apart, that far away. So you have 3 curves, and where the 3 curves intersect gives you your position. Now, looking at this diagram here, this is roughly what you see, and you notice that where the 3 intersect, that is where you are. But normally you'll see that there is an error circle in that area. So that means there are actually 2 positional values. One is the correct value and one is the wrong value. Right, when it comes to spacecraft navigation, and we want to use pulsars, in order to do that, the way it works is that you need a telescope, radio telescope, to actually track and determine when the pulses of the pulsar occur. And when you know what the time is, you will transfer that information to the solar system barycenter. The barycenter is, you might say, the center of gravity of the solar system. And let's, for argument's sake, it's 92 million miles away, so you know the time taken from Earth to that point is 8 minutes. So that when you have your spacecraft somewhere somewhere in the solar system, what you're looking for is to get your 3 pulses from 3 distinct pulsars, and by triangulation you can determine your particular position. Now, in order to do that is you calculate where you think you might be. That means we've got ground stations, we've got computers, we can work out where that satellite is in space. So we know that at what time they should receive a signal. But because of the distance, the communication time between Earth and where that satellite is, there's likely to be an error in the computations, likely to be an error where they actually think they are. So there will be a time difference between the expected time and the actual time at which that spacecraft receives the signal. And again, now, not going into the mathematics, but you can work out what that error is, and you can correct for it and determine the actual position in space. Now, 2018, 2019, there was the NASA sextant experiment was placed on the International Space Station in order to determine how accurate the X-ray pulsar navigation can be. And the results obtained were to an accuracy of between 2 kilometers to 19 kilometers. Now, the ISS is probably not a good example of testing for using this method of determining where you are, because our radar and our communications are far better than using pulsars. We know their position to the accuracy of centimeters. 2 kilometers is just not good enough. So, but if we were to use such a system, then using the barycenter, the center of gravity of the solar system as a point is not a really good way of actually doing it. What you would want to do is to actually use the time of which the signal from the pulsar arrives at the Earth's center, and this is the observatory which records the signal, and you're interested in this distance delta S. And if you multiply the difference in time at which the pulsar arrives, it's computed to arrive here, and the time at which it arrives at the satellite, you can measure what that value of delta is. Now, for interplanetary navigations, it's slightly different. You do need to use the barycenter. Now, again, basic reason here is that if you send a spacecraft to Mars, as an example, communication time between Earth and Mars can be anything up to something like 30 minutes. Now, if you are, this is now, if we're going to send a manned probe to Mars, yes, we can fire it over here, but when it comes to around the Mars region here, we need to fire the retro rockets to slow it down, put it into orbit around Mars. Now, because of the time in communications and the distance involved, we're likely to be more than 20 kilometers out in our estimated position of where our manned spacecraft is. If you use pulsars, you can get an accuracy to within about 20 to 30 kilometers. So therefore, you will have a much better idea when to actually fire your retro rockets and put it into orbit around Mars. Right, let's say then a little bit about pulsars for ship navigation. So this is pulsar, I'll explain that in a minute, but basically pulsar emits radio waves, X-rays, various electromagnetic energy in the various regions of the electromagnetic spectrum. And by the time those waves reach us, they are actually parallel waves, as illustrated here in this diagram. Right, these are parallel waves, and what we are interested in calculating is the difference between the time at which the pulsar reaches the Earth's center and the position of the observer. And again, multiply that by the velocity of light, you will again get this distance delta s, and that is what you need to calculate. You use that to calculate the position of where you are. Right, pulsars themselves. We need to say a little bit about the evolution of stars. That they start a large amount of gas which slowly condenses, and eventually it will produce a small star or a larger star. Now, when the star comes to the end of its life, the nuclear fusion process within that star changes from converting hydrogen to helium to other elements. So the outer parts of the star expand, and it stops when the thermal pressure due to the expansion is stopped by the gravitational force. So you're going to have a series of expansions over time. So if we take our star, that's a white, it'll end up as a white dwarf. It will not, there won't be a bang, and calculations show that if a star has a mass greater than 1.4 times that of the Sun, it'll end up as a neutron star. And if the mass is greater than 3.8 times the mass of the Sun, it'll become a black hole. And when that actually, when this, let's say if we're looking at the neutron star or the black hole, when that explosion occurs, that happens when we start going from an exothermic reaction, because when the nuclear reaction goes from hydrogen to helium, energy is emitted. But once we go work our way through the various elements, we'll end up trying to produce iron, which is an endothermic reaction, meaning it wants to collect energy from the star, and therefore that causes it to collapse. Now, a pulsar is effectively a rotating neutron star. The only difference being is that the radiation beam and the axis of rotation point towards the Earth. So we actually see this pulse. And the Crab Nebula here is about the most famous pulsar of all. Right, so let's just literally explain this contraction and the actual rotation speed of a pulsar. If you have a skater and has her arms stretched out like that and brings their arms together, you know very well that they start rotating faster and faster. So just on that very simple sort of experiment using conservation of angular momentum, the rotation rate is going to be about 9 times faster when you've got your hands together as compared to when you have your hands stretched out. And some very, yes, there's a lot of numbers there, but very basically is that the sun rotates, has an orbital period of 28 days, which is 28 days multiplied by another large number, which gives you the number of seconds. Now we also, you know about the atom, and you've got a nucleus and you've got the electrons going around it. And we have here the Bohr radius, which is again this number here, and the neutron radius, which is all of that here, so that when a sun expands and blows, all you're left is the neutron radius here. And the reduction in the radius, or between the Bohr radius and the neutron radius, is 10 to the 5. That is 100, 1 with 5 noughts under it, that's 100,000. So if we apply that to the sun, so if we use that factor, about half of the gas is going to escape into space. The sun will collapse to a radius of about 7 kilometers. Now, and if we apply now the conservation of angular momentum, very simply, we know what the mass, we know that the ratio rotation period, if we apply that because it's angular momentum, it's the square, the radius, so we will get the rotation period for the sun if it happened to be a neutron star, and it'll rotate over 4,000 times a second. But with the Crab pulsar, which has a rotation period of 33 times a second, and if you work out what the value, what this ratio is, this mass times radius square, you will actually find that the size of the Crab nebula is between 7.4 and 9.6 kilometers. Now, how do we know the mass of the pulsar? Very simply, if the pulsar is there in space and if there are any orbiting objects fairly close to that, we can see the disturbance in the orbit, and from that we can work out what the mass is of the pulsar. Now, when it comes to using pulsars for ship navigation, we're not in the business of looking for new pulsars. We will actually want to select about 50 suitable pulsars for navigation purposes. The majority of the pulsars lie in this region here. That is the ecliptic equator. Sorry, that is the galactic equator here. Most of them are in there, and if you work out where they actually are in groups of stars. So for pulsar navigation, ship navigation using pulsars, we probably need about 50 well-behaved or well-known pulsars for that purpose. Now, just regards to pulsars themselves, there are two or three types of pulsars, but we are interested in millisecond pulsars, which have an orbital, that means their rotation is more than 1 rotation per second, and the Crab pulsar is one of them. Or if their rotation period is around about a second, it's called a second pulsar. Now we have about 3,000 such pulsars have been detected to date, and a square kilometer array is expected to identify another 20 to 30,000 pulsars. As I said, the astronomy community is interested in pulsars because it's interested in gravitational waves, it's interested in black holes, interested in how the universe has been created. That's not what we're interested in. We just want to select a few pulsars, know what their orbital rotational periods are, and work out where the actual ship is. So one possible candidate is this one here, and that's not too far away from the W of the Great Bear. No, is that the Great Bear? Perseus. Right, so that is one, and what we're interested in is the difference here, as I said, between time of arrival at the observatory and at the ship. Also, we have the Crab Nebula, and that is the Taurus the Bull, and those are the two horns, and just about in this region there, that's where the Crab Pulsar is. And it's about 1,000 years, it means it was first detected about 1,000 years ago. Now, with regards to our application, we're going to use some form of telescope, and if we have the right telescope, this will be the field of view, about 2-degree field of view, and in that field of view, you might be 1,000, 10,000 stars. Now, an ordinary, if you use a person trying to identify the pulsar, they're going to spend many hours trying to say, well, that's the pulsar, forget about the rest. So we've developed, or the astronomers have developed, machine learning algorithms which say, well, we're only interested in this type of object, forget about the rest, and they can reduce the time of identifying the pulsar in this region to literally a matter of a second. Oops. Let's go back again, right. Wrong way. Okay. So we have so what's the processing pipeline? Well, first of all, we go and we need to acquire this pulsar. So that's your data acquisition. Now there is a lot of cosmic noise. So and there's also local noise as well. So the first thing we need to do is to get rid of the radio frequency interference. So when it comes to your ship, I'll go and mention what those interference noises are, but we need to get rid of those. And if we look at what work's been done in the maritime or the marine seismic area, it will take about 2 to 3 weeks to actually train a machine learning algorithm to identify what those radio interferences are. And once you've done that, and you go to the pre-processing removing of that, every time you go and identify a pulsar, you can literally eliminate that noise in a second. Now that's that particular area. This is the marine seismic area. Now the dispersion, you need to get rid of that as well. Very basically, you have when the signal passes through space, there's going to be a lot of cosmic noise. Now, I can see quite a lot of you are roughly my age, so when you were teenagers, and when you got your 625 televisions, first ones, you had to use a dial to go and tune into your station, but you heard all that hissing noise, didn't you? Well, that's your cosmic noise which you've got to eliminate. So effectively you might say, well, this is what you've got here. That's the pulsar signal, and this is all the noise are over there. But in order to establish what that signal looks like, you need to improve the signal to noise ratio. Now the advantage we have is that we know the pulsar signal. So we don't have to go through all the laborious tools, methods of actually improving the signal. We can do it much faster. But obviously, if we're looking at the maritime environment, we have to optimize the tool because this area of work has not been done yet. Right, some of the examples of radio frequency interference. Well, we've got the natural environment, and that's obviously your wind, your currents, your earthquakes, lightning, rainfall. You have the ship environment, well, that's your engines, that's the vibration, electronic equipment, so forth. Then you've got your crew, or if you're on a cruise ship, it's your passengers as well, and they're using their phones and computers. You've got broadband networks, satellite networks, and then you've got complex noises. Well, if you are in the English Channel, you've got a lot of ships around you, or if you're coming close to port, you've got all the activities around the port. An irregular background, again, are the aircraft which are communicating with ground stations. You've got the mega satellite constellation, Starlink is one of them. The Chinese are going to have a couple, of about 10, 20,000 satellites. So there's going to be a lot of noise, which you have to eliminate in your analysis. So basically you've got, this is something like about 120 pulses within an actual noise. And one way in which we can eliminate that is to go and normalize that data. So you have a maximum value, a minimum value, and you can basically squeeze that so that you get something like this. And what you're after is basically to get this type of profile for the pulsar that you're interested in. Right, so with regards to telescopes, we've got, well, there's the Parkes telescope over in Australia, 64 meters in diameter, weighs about 1,500 tons. In no way are you going to have one of those on board a ship. But we can either have an antenna which has got a large collection area, which again, there isn't the sort of space on a ship or on a cargo ship. So what you can do is to have several small antennae scattered around the ship. So you'll have different signals, which will be like this. And what you will do is you'll use fast Fourier transforms. And now don't ask me to explain how they work, because I don't know yet. But you will end up with a signal something like that. But these very large telescopes can get a stable signal like that within about 60 seconds. But that's if you are starting looking at a pulsar which has been identified, but we don't know anything at all about it. So for the ship environment, there's some possible locations where you can put an antenna, or you could use a phase array. A phase array is basically a number of sensors within a parabolic antenna which will collect all the information, and you'll end up producing a strong signal as if it came from an antenna of that particular size. Another thing you've got to think about is the stability of that phased array or that antenna. And obviously you've got to consider some of the motions of the ship. You've got there the rotational motion or the translational motion. So on board your various ships, your cruise ship, you've got stabilizers which will try and keep you relatively stable, but you'll still feel the waves. But in this case, the solution lies with something like, a naval gun, which has got an electromagnetic or a purely, truly electronic system which will keep that platform stable. So that's the sort of thing that you need. Because as we said before, if that antenna is moving around, you will not be able to focus on the pulsar that you want to use for navigational purposes. So these are just literally some examples of phased arrays. Now, phased arrays can be placed anywhere on the ship, basically on the superstructure, away in looking in a particular direction, and you can come up with different types of architecture. So you can have a dual band, you can have a multi-frequency phased array. So these are just some diagrams of where you could locate them. But I think you will probably find they will be within this sort of area here. I mean, that's a radar system in there which is stabilized and doing its work. So again, just literally looking at some examples here of phased arrays, and if they are all pointing at different directions, the area of the antenna will be basically the baseline going right across. So you might have several sensors, or very small sensors, placed around the ship. Now if you have more than about 12 of these around a large ship, being 300 meters in length, you'll have a computational problem. But as I said, at the end of the day, what you want to do is to get a stable pulse and measure this particular distance. Now going on to a little bit about astronomy and some of the things that you need to know in order to do the calculation. First of all, the Earth isn't a sphere. It's got all sorts of funny shapes, but it is the best, easiest mathematical representation of it is an ellipsoid. And if you're navigating, if you're going from A to B along a great circle arc, just say the distance for a great circle arc between 2 points, for example, is 5,379 kilometers. But if you take the ellipse into account, you can see that the distance is different. So when you're actually navigating, and if you want to save on the amount of fuel you use, you've got to take that into account, because just because you're using a great circle doesn't mean that's going to be the most economical way of going from A to B. But again, I'll come back to this diagram here, but what I'm trying to say is that you have two types of systems. You have the geocentric system, that means that refers to the circle or to the sphere, and you have the geodetic system or computational values, which refers to an ellipsoid. And some other parameters which we've come up are using. Obviously, Greenwich meridian is a reference point, and we need to know the time to the left or to the right, and we use the terminology of hour angle. Also, depending on where you are, you have the observable horizon, you have the inclination of a star or a pulsar, or the declination or the distance from the pole star. So we've come up with the hour angle, we've come up with Greenwich sidereal time, we also have declination. Another reference point is the first point of Aries. Now that's important because every 23,000 years the point of Aries comes back to the same place. But when it comes to doing accurate computations where a star is, then you need to take into account the equation of the equinoxes. So that means that's the wobbly effect of the Earth's, or the Earth wobbles, and also because the axis to go right, one rotation takes over 23,000 years. Now when it comes to why should we be using the Earth-centered system for calculating where the pulsar is? Very simply is that if you're going to send a signal to a point somewhere in space, you're going to have to do a lot of computations to take into effect gravitational effects, the relativistic effects, and other things like that. And then you've got to go and bring them back again to calculate where your ship is. It's much easier just to go and use the classical system which we have, latitude and longitude. So you might as well have, you don't have to use something on the actual, you don't have to use Greenwich Observatory. It could be any observatory, but what you need to do is to is to know where the position of that observatory is on the pulsar Earth center line, and you do the same thing for the ship. You know the time at which that is observed there. You know that time there, so you'll be able to know what is the time difference, and hence the distance between this distance here, delta S. Or what you want to do really is you want to know the distance from there to there, which we've called ds. And the calculation here is straightforward right-angle trigonometry. You've done that at school, haven't you? So that's something very simple. Right, some other simple things in order to do a calculation. Well, when you've got a triangle, you know the three sides, but you want to determine a side. If you want to determine the value of a side, but you've got two adjacent sides and an included angle. You probably have learned that at school for your GCSE, in our case GCEs, and you needed to know that for doing your exams. So there is a similar equation for spherical trigonometry. You have it's just basically this equation here. Okay, that's just take my word, that's the equation, right? I just wanted to show you how similar it is basically in construction to that. Then there's another thing you learnt at school. You probably had a quadratic equation, right? And you know that when you solve a quadratic equation, it's given by that value there. You may have two answers, one is correct and one isn't correct. So what I'm trying to say is, you're using basically school mathematics in order to do the computations. Right, another thing, you may have done something about vectors in schools. So if you have two vectors, you can determine, if you know the distance, the length of those vectors, you can calculate the angle between the two vectors, which is given by this equation. And if you go and substitute your trigonometry function in there, you find out, you cross those out, and you find you have that expression for the angle you want in terms of your x and y and z, which is what you have for your GPS system. Or alternatively, you go and use that equation I showed you before. So you've got two different ways of doing the calculation, and in theory you should get the same answer. And then something which you probably remember from school days, determinants, matrices. And you just basically use that to do the computation. So again, what I'm trying to say, it's not rocket science. Right. So, time there when I did the computations, you take, I've taken about 4 or 5 pulsars, and they're not necessarily the best pulsars, but literally just to use them to see what sort of answers we get, what sort of problems we're going to get. Well, you can't use the crab pulsar because it's below the observer's horizon, but the other ones you can. But notice that pulsar there and that pulsar there, this one's very close to the observatory or the reference observatory, and that one is very, very close to the pole. So anything which is close to 0 when you're subtracting or adding, or anything which is close to 90, it's not likely to be a good choice. So you need to do computations like that in order to determine what are they usable or aren't they usable. I mean, there's that one in red here, and look at the time and difference measurement. 4 times 10 to the minus 5 seconds. I'm assuming, of course, you've got an atomic clock on board the ship, and you can measure these time differences, which gives you the corresponding delta S values, and these are the delta S values, and if you plug them into the equations which you have the x, y and z's, or the one using the angles, you'll be able to come up with an answer like that. So from the simulations which have been done, which I've done, and I've used a Monte Carlo simulation. So what does that mean? Basically, so I've said that the error in measurement is about 3 microseconds, plus or minus. And I'm using a random number anywhere between plus 3 microseconds and minus 3 microseconds. And I'm not going to use 1, 2, 3, 4, 5, 6. I've actually multiplied it by 1,000. So I've actually got a random number, which is a usable number. And I get a whole string of random numbers. And I use the calculation, and I do the calculation, find the average value at the end of the day, and you come up with positions. And what we use the example, going back to the original scenario, you're in the Bay of Biscay, that's where you lost communications, and this is where you are. That is your real value. But you find that when you do the computations, that you are within a fairly close position to the actual true position. Means where you should, this is where you think you are, this is the actual position. And that is the error in your computations. Now another thing you can do, you can use a single pulsar. You don't have to use 3 or 4 pulsars to determine your position. And this is worked on the assumption that a ship will travel no more than about 25 knots. So if you do a measurement every 2 minutes, the ship won't go more than about a nautical mile. And the motion that you take into account is the motion of the pulsar, means the Earth's rotation. It does about 1,000 kilometers an hour. So it's that motion which you can use, and you can do. And going back to your x, y, and z, you've got to have three unknowns, x, y, and z. With regards to your angles, you know the position, the radius, because the ship's only going to move 1 kilometer. And if you knew your radius an hour ago, the radius is not going to change by more than 10, 20, 100 meters. So you can say forget about it, because you know the accuracy that you're seeking is of the order of a nautical mile. So you literally have 10 points, and you take the measurement of the pulsar at time 0, at time 0 plus 2 minutes, plus 4 minutes, and you just work your way, and you get a number of points. And when you do analysis, you want to get the best line passing through those, and that will give you the best value starting at the time you start the measurement to where you were 10 minutes later, or where you're going to be further afield. It's interesting what happens if you actually is not going to go in a straight line, but you're actually going to start maneuvering. That gets a bit trickier. Right, so to summarize, these are the results that you get if you use 3 or 4 distinct pulsars. You get errors in latitude and longitude of less than 1 kilometer. If you use the but you use the Monte Carlo simulation here, that means you've done about 2, 3, 4,000 simulations and you found the mean value. If you just use one value for a that means you only just use one computation over the 10 minutes. These are the values you get here. And if you use a random sampling, that means you're going to run about 200 simulations with different starting points, that means different time of arrival errors. You'll get this, and notice that that value there is about as good as what you'll get with a sextant, and that is just about what you get by the best people, the skilled navigators using sextants. And if you were to, so this uses your theta and your phi, where you only need 2 values. You're solving for 2 values. Radius has hardly changed. If you use x, y, and z, again using random sampling, 200 cycles, you get this figure, which is, well, it very much depends on how your random numbers generate. Probably I didn't use enough random numbers, but they should. This number here should match roughly those numbers there. because they originate from the same point. So, just then to finish, that's a summary of the results. ESA has issued an invitation to tender. This is a next round, or they're repeating the round which we didn't succeed last year. There's a consortium of Southampton University and Oxford University, and if we're lucky, we will get the award to actually investigate those sort of things which I've mentioned. So we'll know by around about summertime. So that's the end of my talk.